Okay, so let's review functions and some other stuff about functions, talking about domain and range and how to find those. We're also going to look at piecewise functions and the difference quotient. So first, let's make sure we understand what is a function. Well, in order to understand a function, we need to understand a relation, since a function is a specific type of relation. So what is a relation? Well, a relation is any two elements, those elements are usually variables, related to each other by some rule. That rule is usually an equation, or in the case of a piecewise function, multiple equations. So that's a relation. So a function then is, again, it's a specific type of relation. So it's a relation in which, a relation which assigns each element, that element we usually think of as x, however it does not have to be x, in some set of elements, to exactly one element y in another set of elements. So let's look at a non-mathematical example of, well, what exactly does this mean. So I'm a big fan of soccer, so I'm going to give you an example of soccer. So let's say we have, these are, this we'll call set A, and this is the players. So let's say we have Tim, Jill, and Brian. Brian's a great name, so we're going to use that one. And then over here, this will be set B, and this will be the number of goals. So let's see, and let's say this is number of goals in a game. Again, this is just an example. So you could have 0, 1, 2, 3, 4, and so on. So if this is a function, and this is for a particular game, let's say Tim had 0 goals, Jill had 2 goals, and Brian had 1 goal. So now this is a function because each element here in set A goes to exactly one element in set B. So we could say that this is goals as a function of player. So that's a function. Now, just to show you real quick, if this wasn't a function, or how we could make this not a function, would be if, let's say, Jill scored 2 goals, and she also scored 3 goals. So obviously that's impossible in a game of soccer, but that would also make this, it would still be a relation, but it would not be a function now. So we're going to take that away so that we keep it a function. Another thing to point out is note that in order for something to be a function, all of the elements in what we're calling set B, which is goals, do not have to relate to an element in set A. So the only thing that has to happen is every element in set A does have to relate to one and only one element in set B. Okay, so how do we determine if something is a function? I know this is the burning question in your head, and hopefully most of you, if not all of you, already know the answer. The easiest way is if we're given the graph of a relation, then we can look at the curve and we can do what's called the vertical line test. And this is how we can determine is a relation is a function graphically. And I'm not going to give you an example of this. Hopefully you guys remember. If you have questions on this, please ask me in class. But basically we're looking for, does a vertical line cross the curve more than once? If it does, then it's not a function. If it doesn't, then it is a function. Okay, well, what if we're not given the graph? What if we're given the equation of the relation? So then we can solve this equation analytically So what do I mean by that? Well, if I have this equation, negative x plus y cubed equals 17, if I solve this for y, I can determine is y a function of x. So if I solve this, I would add x and take the cube root of both sides, so we're going to end up with, so again, sorry about that, if I solve this, I end up with y equals the cube root of 17 plus x. And so the key thing to notice is that there will be one y value for any given x value. Therefore, this will be a function. Whereas if I look at this other relation here and I solve this for y, now when I solve, I'm going to end up with y equals plus or minus the square root of 17 plus x. So notice that because of this plus or minus, for a given x value, I'm going to have two different, or potentially two different unique y values. Therefore, this is not a function. Another way to look for if something is a function, if we're given a set of points, again here what we're looking for is for a single input value, is there one and only one output value. So if I draw my A set, this would be 3, 5, and 7. Those values are coming from here. And if I draw my B set, I'll have 4 and 6. Those values are coming from there. And so now I can see that 3 goes to 4, 5 goes to 6. Okay, again, I apologize for technical difficulties, but let's look at this again. So the 3 goes to 4, the 5 goes to 6, and the 7 also goes to 4, but that's okay. What's important is that for each input, it only goes to one output. So this is going to be a function. Whereas if I look at the example here, we do A again. Here we have 4 and 6. And for B, we have 5 and 6. And so, again, we get these from the values there are A, and here are the B. It's okay that I have 6 in both of them. Don't get confused by that. That is just a coincidence. But what's important to see is that 4 goes to 5 and 4 goes to 6. 6 also goes to 6, but what is causing this to not be a function and to just be a relation is the fact that 4 goes to both 5 and 6. So therefore, this is not a function. Alright, next thing we're going to talk about are domain and range. So domain is what we call the input values. Most of the time that's x. Again, it does not have to be x. It can be whatever the independent or input variable is. What we're looking for, what we're talking about though with the domain, or how we want to define it is the set of all real numbers where the expression is defined. And a couple of key things to notice here are real numbers and where it's defined. So basically what we're looking for are where would it not be defined and where would we not get real numbers, and those are going to be where the domain does not exist. Graphically, it's really easy to determine the domain. We read it from left to right, so the lowest x values to the highest x values. If there's gaps, that's okay. And most of the time we're going to write our answer in interval notation. So remember, that's parentheses and brackets. You can also write it out in words, or you can use inequality notation. Interval notation is just usually nicer and quicker and cleaner. So that's what we're going to focus on that. So an example is if I have f of x equals 1 over x plus 1. Well, here I don't have the graph. So I could graph this if I want by hand or on my calculator. However, sometimes that's not always the easiest way to do it. If I have the actual equation of the function, the easiest way to think about the domain is where does it not exist. And so again, basically, where is it not defined, or where will I not get real numbers? Well, it won't be defined if I divide by 0. So what is going to make this have a 0 in the denominator? Or if I have an even root of a negative. So obviously this function doesn't have a root, but if I had a square root or a fourth root or a sixth root, any even root of a negative, then I'm going to get non-real numbers. So in this case, the only thing that's not going to, where the expression is not going to be defined, is if x is negative 1. So my actual domain then would be negative infinity to negative 1, negative 1 to infinity. That's interval notation. Again, the parentheses mean that we do not include the number. If I had brackets, then I would be including the number. Think of parentheses as your open circle, brackets as your closed circle. Another way to write this would be shorthand. That's the symbol for all real numbers. X does not equal negative 1. I'd prefer if we focus on the interval notation, however this is acceptable as well. Range is the output value, so this is most of the time the y. Again, it does not have to be y. It's whatever the output of the function is, though. This is what we usually call the dependent variable. This is more difficult to figure out analytically, so most of the time we just do this graphically. So we read from bottom to top, the lowest y values to the highest y values. The other thing, or the last thing to keep in mind, both when we're talking about domain and range, is to use some common sense also. So what do we mean by that? We mean, well, a lot of times we'll be dealing with a word problem or a problem that pertains to some real-life situation. In that case, there are limits on the domain and the range that may not be actual limits to the function. You know, think about time, for example. We usually don't use negative time, so that would restrict, if time was your input value, that would restrict your domain. So that's what we're talking about with using a little common sense. Sometimes a question might ask for the domain of the function, and then you might see something where it asks for the practical domain of the actual application or the problem. And that's where you would have those two different answers.